Hello, everybody. This is Isabel Casso. I am a PhD student at the University of Lille in France. I am part of the Cognitive and Affective Sciences Laboratory, SCALAB. I'm going to present to you our preliminary study that we conducted in collaboration with the Crystal Laboratory, also from the University of Lille. And it's about the intonation classification of imagined speech for brain-computer interface applications. So I'm going to start by presenting you my program for my presentation today. I'm going to start by talking about some theory on imagined speech and prosody, and also on brain-computer interfaces. We'll introduce our objectives, our methods, and we'll finish with our results and discussion. So we humans are capable of producing different kinds of speech. We call over speech to the auditive output we create after articulating, moving muscles, and directing air through our vocal cords. But we can also speak without involving any motor actions, with no muscles, no articulations. This speech is voluntary. We call it imagined speech. And how is imagined speech produced? According to the dual stream prediction model by Tian and Popu, speech is an articulatory trajectory planned in the left inferior frontal gyrus, right here. And this trajectory can either be sent to the primary motor cortex, here in red, to produce overspeech, or it can bypass the motor cortex to be simulated internally. This simulation triggers two events, a somatosensory event and an abstract auditory representation. Why are we interested in imagined speech? Detecting and decoding imagined speech can serve for developing tools for individuals who cannot articulate. Moreover, decoding prosody of imagined speech would allow a better adaptation of these tools as communication aids. And why prosody can better adapt these tools? Prosody is an important characteristic of speech, which allows us to convey emotion and meaning. We know we have two types of prosody, linguistic prosody and emotional prosody. Linguistic prosody concerns the domains such as rhythm, intonation, tones, and pauses, which are conveyed by variations of the fundamental frequency, duration, and intensity of our speech. And emotional prosody actually, through these parameters, expresses emotion. And the focus of our study is linguistic prosody. But prosody impairment can affect communication because interlocutors cannot interpret intention. Generally, as you can see in this image, we have different variations when we speak and our fundamental frequency to convey social cues. Then how can we have access to imagined speech? We can use systems like brain-computer interfaces. A BCI is considered as a closed-loop system, which consists of the recording of brain signals, their decoding, and their translation into a command to provide feedback to inform users about the recording brain activity. Its applications can range from handicap aids to text editors and video games. So how can we employ the capabilities of BCI to develop communication tools that can work based on imagined speech, more specifically in the prosody of imagined speech? So first, we must choose a recording method that is non-invasive and user-friendly. So we chose EEG, which is a common brain signal recording method. They are caps with metal pieces that serve as conductors between the scalp and an electrode that measures the electrical activity of the brain. So this recording method has been used before in BCI studies that decoded imagined speech. More specifically, Deng and colleagues, they classified the rhythm of 2 different syllables. Nguyen and colleagues, they classified words and vowels. Sarmiento and colleagues, they classified different Spanish phonemes. And Lee and colleagues, they classified tones 4 different Mandarin lexical tones. So based on these studies, the literature on the production of imagined speech and the literature on prosody, we define 3 brain frequencies of interest: delta, alpha, and beta. To have a BCI as an end product, we must focus on the decoding task. So first, our objective is to decode intonation from EEG signals of imagined speech. We chose to decode 2 intonations, affirmation and question, where the affirmation is our control condition. We chose 2 syllables, ba and da, with no semantic content to not trigger cortical activity linked to semantic processing. So we have 4 different conditions: ba and da as affirmations and ba, da as questions. Once we defined our decoding objective, we designed the experimental paradigm. Our 6 participants first saw a fixation cross for 1 second, afterward the prompt for 1.5 seconds, and after the prompt disappeared, they had to repeat it with their imagined speech. As you can see here on the left, this video shows us an example of what our subjects saw. Okay, so for the analysis, we chose the signals from these 6 electrodes that were also used by Lee and colleagues to classify imagined Mandarin tones. We epoched our signals considering the 2.5 second production phase plus 0.2 seconds prior to production onset. Our decoding phase consisted in the selection of the time frequency representation in a frequency band to train and test our algorithm, composed of a common spatial pattern filter and an LDA classifier. We did this for every band you see in this list. Now, about our results, as you can see here on the right side, we present a graph of the obtained classification accuracies. On the x-axis, we have the imagined speech production phase in seconds. On the y-axis, we have the frequencies at which we perform the analysis of the signals from our region of interest. The color bar lets us know which time frame and frequency have an above chance level accuracy. The calculated chance level was 55%, and the highest score we obtained was 57%. This high score was obtained in 2 occasions and different bandwidths. Early on the production phase at around 0.1 seconds, between 7 and 12 hertz, that is within the alpha band, which could be related to the planning phase of the speech production, and at 1.8 seconds, between 16 and 20 hertz within the beta band, as you can see here, which could be related to other processes unrelated to imagined speech. To better understand our results, we obtained the topographic maps in timeframes for these two bandwidths. These maps show the electrical activity of the 64 channels of our EEG cap, and the color bar lets us know the registered voltage at every time frame. On the left, we have the maps of 7 to 12 Hertz from 0 to 0.4 seconds for the question and affirmation intonations. We can observe a contrast in the region of interest we chose, which is up here on the right for reference. We have on the right, also for both intonations, the maps of the 16 to 20 Hertz bandwidth from 1.6 to 2 seconds. But we also observed a difference in other electro groups, as you can see here in the occipital region for both bandwidths. To sum up our results, we can say that intonation of imagined speech could be decoded using EEG, and spectral features seem an appropriate feature for such task. Especially the results we found during the early time window are consistent with literature on speech production. Some remarks about our results are that due to the limited literature on prosody, we based our electoral region of interest on the study of imagined tone production. It is known that as a non-invasive recording system, EEG tends to have low spatial density compared to other systems like electrocorticography, which is an invasive system. We didn't get significant results with the delta band, which is considered to be important in the imagined speech production. We think it might be because the stimuli might have been too short for this very slow frequency band. We also observed high variability subject to subject. We think this was due to the fact that our task was not time locked. So for future studies, we found that blind classifications, this approach like the one we did, is not sufficient to develop BCIs. We need further research on the involvement of the delta band in prosody production, as well as assessing other frequency bands and regions of interest. Finally, we need to design a time-locked task, being careful to not trigger cortical activity that is unrelated to speech production. So this is the end of my presentation. Thank you so much for your attention. Thank you to the organization for giving us the space to present this study. And I would also like to thank all of my collaborators for all their feedback and their advice throughout this study. Thank you so much again. And if you have any questions, please feel free to ask.